Good morning, everyone. Welcome to this webinar on higher levels of automation and artificial intelligence in air traffic management. We have been working on within SESAR on a number of webinars. We've already done a couple on use space and drones, on exploratory research, on nurturing young talent, on digital sky forecasts, on the impact of the COVID-19 crisis, the recovery of that, and in general on resilience in air traffic management. And this webinar now is part of a series in the context of the Digital Academy webinars. What you can see is on our website, if you go to news and events, past events, you'll see the recordings of those webinars that have already been done. Then the Digital Academy webinars. Let me check something. Okay. The Digital Academy webinars consist of a number of topics. So it's the European ATM master plan that was already concluded on the 30th of June. We have two sessions on towards higher levels of automation on the today and on next Friday. Then we have a consolidation of use space results, the communication, navigation, and surveillance, virtualization about remote tower, and about the airspace architecture study, changes in architecture setup, trajectory-based operations, and SESAR in the environment. All those are going to be planned after the summer break. Within the ATM master plan, we have identified different levels of automation which are guiding us through the development of the, let's say, the innovation of the air traffic management system. And even though the master plan has these high level, let's say that the 6 levels that are identified here allocated to different functions and different levels of automation within those functions, we have been looking into that in more depth, and that's what we're trying to share here in this webinar. So last summer, the scientific committee of SESAR has organized a workshop with all the leading experts inside and outside SESAR on higher levels of automation. That led to an advice and a report that was handed over to the SESAR Joint Undertaking, which will be made available publicly through our website very soon. So the results of that we will be discussing here in 4 different sessions. So the first one is a warming up. It's an example from NETS about higher levels of automation in time-based separation. So it's a safety critical environment during the approach. Dual presentation by Andy Shand and Claire Pugh, followed by an in-depth explanation of the different types of artificial intelligence. So first of all, what is artificial intelligence? What is machine learning? What is big data? How does it all relate to each other? And what are the opportunities that we see in aviation? This will be presented by Professor Jesus Garcia from the University Carlos III de Madrid, followed by the third presentation from Mark Baumgartner from IFATCA about the human-machine hybrids approach. And we conclude here with a presentation by Guillaume Soudin from EASA about the perspective of trustworthiness of artificial intelligence. So this is about how do we certify, how do we make sure that it's actually safe if we go to higher levels of automation. On Friday, I'll not go into this in detail, but just as a teaser, we go more into the examples. So 4 more examples about different areas of air traffic management where we see an application of artificial intelligence emerging. If anyone has any questions, feel free to share them. There is on the right side of your screen the questions tab where you can put your question online. We will have at the last 15 minutes some time for questions and answers. But meanwhile, your questions will also be answered by the speakers. And then that was my introduction. I give the floor to Andy and Claire.
So good morning, and thank you, Ruben. My name's Andy Shand. I'm joined today by Claire Pugh, who is Optimized Separation Concepts Lead in NAT's R&D department. It's a pleasure to speak to you today about our experience of automation with time-based separation for final approach. So Claire, can you bring up the next slide? So I'll briefly talk about the TBS tools concepts, the benefits and the elements of the tool that we put into operation. And then I'll hand over to Claire, who will cover the tuning of the tools and the safety assurance. I'll then come back very briefly to finish off by looking at the future roadmap for the tools. So next slide, please. So firstly, a bit of background. TBS was developed and deployed at Heathrow in March 2015. Prior to that, we'd been heavily involved with SESAR development of the concept, and we then worked with Leidos, formerly Lockheed Martin, to industrialize the concept and work with our controllers to develop something that was actually quite simple in terms of the HMI. The original system provides separation to the final approach fix, in our case 4DME, using UK 6 wake vortex categories. And then it was updated further in 2018 to something we call enhanced TBS, which uses RECAT EU wake vortex categories and provides separation and spacing indicators to the runway threshold, both for wake and for runway occupancy. And it's true to say that the benefits have surpassed our expectations, and the system has been in continuous live operations since March 2015. Next slide, please, Claire. So TBS was originally implemented and developed to provide resilience to the capacity that's lost during strong headwinds. And it's actually done this very well. I mean, we've seen a 62% reduction in delays due to headwinds. That's about 80 to 90,000 minutes of ATFM delay per annum at Heathrow. And we've also avoided the tactical flight cancellations that used to occur on strong headwind days. But with the addition of RECAT EU, optimized runway delivery and runway occupancy tools, enhanced TBS has delivered even more benefit. Now, the fact is the Heathrow controllers were good before the tools were introduced, but we're now consistently delivering much more precise separations and spacing, which translates into increased landing rate. And on average, Heathrow's landing rate has gone up by 2 and in headwind conditions, 4 or more movements per hour. Interestingly, we measured the time interval between arrivals before we put the tools live, and then for the same sample of arrivals after the tools were live, and it's equivalent to giving the airport another 30 minutes of arrivals per day, which has been absolutely huge in terms of the performance improvement. And importantly, this is increased capacity has allowed lower airborne holding, saved about 15,000 tons of fuel per annum, or 47,000 tons of CO2 per annum. And even though the aircraft are closer together on final, go-arounds and wake encounters have not increased due to TBS separations. Can we move on to the next slide, please, Claire? So the basis of the tool is shown on this slide. So we started off collecting, it was actually 5 years worth of data supported by SESAR and Eurocontrol, 5 years worth of wake vortex measurements, both in ground effect and out of ground effect. And that provided the basis for the safety case. Now, other people don't need to do that now. We've already done that collection, which has proved the case for TBS. We work very closely with our controllers to create a simple HMI, which we then industrialized and implemented. And one of the key things we needed to know, of course, is exactly what the winds were doing on final approach. So we created something called the Glide Slope Wind Condition Service, which uses downlinked Mode S data to create a very accurate and real-time picture of winds on final. In 2018, we then updated the system to add RECAT EU wake rules, optimize runway delivery and runway occupancy indicators, and that system has now been running since continuously since March 2018. So at this point, I'll hand over to Claire, who will talk about these parameters in more detail and how they enable controllers to more precisely deliver the minimum safe separation and spacing to the runway. Claire.
Thanks, Andy. Yes, as Andy was saying, there's a number of components that fit within TBS and what's known as ETBS, Enhanced TBS, where the efficiency depends upon the tuning of those parameters. The animation shows ORD, Optimized Runway Delivery, which calculates the anticipated distance compression as the lead aircraft slows to its landing speed. As the lead aircraft approaches the threshold, the amount of compression reduces until at the threshold, the separation is that of the required threshold separation, and the indicator shown by the pink line. For some pairs of aircraft, the runway occupancy time, or the ROT, is actually the larger constraint, and therefore the ORD compressions is added to the ROT separation rather than a wake separation. And in this case, the separation indicator is given as a green line, with the pink one being suppressed. ORD enables the efficient delivery of the separations at runway threshold, but in order for this, the parameters need to be tuned to be efficient, as well as meeting the safety requirements. For ORD, speed profiles per aircraft type and over different conditions were data mined to provide this tuning. Although data mining is used in the current version of ETBS, through the SESAR work, we're also exploring the use of machine learning to understand if machine learning could be used to set the parameters of an ORD type tool. That's the ORD part. In terms of runway occupancy, obviously that can also be different per runway. And so this is tuned in terms of ETBS to the actual runway that the aircraft is approaching. In the future, we hope to optimize this further by understanding the factors and the conditions that are affecting that runway occupancy more on a pairwise basis than at the category level it currently is. The tool to provide separations needs to understand the sequence of the aircraft so that it can calculate the separation between a particular pair. This is done through an auto-sequencer, which identifies the next aircraft onto final, which is then used by the tools to calculate the separation at the threshold, the ORD compression on top of that, and then displays the appropriate indicator, be it a ROT or a wake indicator. The parameters are monitored in service and maintained to meet both safety as well as and efficiency requirements, because obviously things may change, and also having in-service monitoring helps us understand how well the system is performing. This is a radar replay of what the controller sees with TBS and ETBS. The animation will show a number of functions which will be highlighted. The indicators are shown on the extended center line. We can see the pink one for wake separation and green for the runway ROT spacing. Bottom left is the TBS table, which gives controllers the TBS separations for the 6 main distance separations. As the wind changes, the TBS separations update accordingly. As shown now, when an aircraft has an indicator, the separation which the indicator represents is given, as well as the distance from the aircraft is from that indicator. And the one that was highlighted, the separation distance was 3.5 nautical miles, and the distance the aircraft was from the indicator was 0.2 nautical miles. Controllers can choose to have lead-in lines on which they connect the aircraft to the indicator, and they're useful, whereas in this case, we've got joining from both the north and the south to the same approach. And it just ensures that the controller is vectoring for the correct indicator. As the one that had the lead-in line from the south of Virgin reaches the center line, although it has a runway occupancy indicator, a green indicator, it's within half a mile of the wake separation, underlying wake separation, and therefore it will display the breakthrough indicator, which is shown by the pink chevron. So as you can see, there's quite a number of sort of tools embedded within ETBS and functions for the control to help the controller manage the separations efficiently. With such a complex system, obviously safety assurance is key. And of course, on all deployments of tools to an operation environment, we need to demonstrate that they are acceptably safe. We do this through assessment, determining the safety requirements that to define and manage the safety performance of the tools. But it would be all too easy to set it to the most extreme variables that we see. It would certainly meet safety requirements, but it does need to be balanced to make sure that we are also delivering efficiently. We also then need to make sure we have the evidence to demonstrate that those safety requirements are met. ETBS contains complex algorithms, mainly the wind forecast or the glide slope wind condition service that Andy mentioned earlier, ORD, and the TBS calculations. A number of these have continuously varying input information, but as we've also mentioned, we also have tuned data and configuration for each of these, which are derived to meet the safety requirements across all conditions and circumstances. Therefore, it's very difficult, and it would also be expensive, to assure the tools through traditional methods of testing through each scenario due to the large number and complexity of the combinations which arise. So there also, because of the dynamic nature of the separation indicators, an error in the tool could lead to an error in separation. For example, maybe the algorithm misuses some input data, and instead of the pink line behind our aircraft, we actually have the red one indicated here, which is closer than we would like it, and it does not meet the safety performance. Because the dynamic nature of the indicators, it means the controller it's harder for them to actually be able to spot these errors. And so therefore the controllers need the trust in the tools to be able to use the tools efficiently. If they were wary of the tools in any way, then obviously they would leave more separation behind the indicators, and it would not be delivered as an efficient tool. In order to provide this level of assurance, outputs from the configuration and the algorithms of the implemented system are compared to the same configuration to an independent reference model. And it's not just that the performance has to be equal, but actually that they are identical. And this enables us to provide the correct level of assurance to the controllers on such that we can use the tools efficiently. Of course, the minute you put the tools in, they go out of date. We do in-service monitoring to ensure that the safety requirements are maintained and that it's operating as we expect. And so if we see anything that's not quite as expected, then adjustments can be made if needed. Also, the parameters of the tools can be updated or retuned, as there may be changes in aircraft types, airline operating procedures, or potentially taxiway exit changes, which may change the ROT spacing. And all these would need to be fed back into the system. So that gives a brief update of the current ETBS system.
Okay, thanks.
I'll hand back to Andy.
Yeah, thanks, Claire. So that's not the end of the story. We're talking to other airports, so the system is being deployed to other airports other than Heathrow, and we're continuing to develop the intelligent approach system, as we call it, through ongoing research activities with the SESAR joint undertaking, adding pairwise separation, which will add even more benefit, and that is work that's currently underway. Can we move on to the next slide? So I think simple to say, based on our experience with time-based separation, we've shown that if you provide dynamic separation tools, they can be driven by whatever is driving the minimum spacing or separation, and make the controlling task simpler and very much more efficient. So I just finish by saying, watch this space. We're continuing to develop the tools and capability. We're very thankful for the support that we've had through SESAR. And thank you very much for listening. And just on the last slide, there's some links there if you want to look at in more detail at some of the concepts we've spoken about. Okay, thank you very much.
Thank you, Andy and Claire. That was very much clarifying how it works in practice, and also introducing the perfect link to the next 3 sessions, actually. I see already some questions related here to what type of methodology or machine learning model are you using, etc. Now, we're not going to answer all the questions here, but also I think it would be really valuable to first have the presentation from Professor Jesus Garcia to explain the different types, methodologies that we have in the context of artificial intelligence. But you also saw already here in this presentation the need for the interaction with the human factor part, the controller that has to interact, and how do we do the safety assessment, the safety certification. So all of that links to the next 3 presentations. So this serves just as an example. I hand the floor to Professor Jesus Garcia. The floor is yours.
Thank you very much, Ruben. Sorry, a moment, I'm sharing my presentation.
Jesus, we're not seeing you anymore. We lost your video connection, but also we're not seeing your presentation. If you have trouble getting your presentation running, I can also run it from my laptop if you want.
Yeah, I think Ruben try to launch his presentation, and then you can read over your slide.
Doing that right now. Okay. Jesus, I put your presentation online already. If you can come back with your video, and maybe you can start a presentation then. I will, and just tell me when you want to change slides. Did we lose him completely?
Hello?
Yes. There I see him again.
Yes, hello, sorry.
Jesus, can
yes.
you? It's all right.
Yes.
I put the presentation on, so maybe you can just use that.
Thank you very much. Okay.
Go ahead.
Okay, so I go ahead. So thank you. Sorry for these technical problems in the last moment. thank you very much to Ruben. Thank you to everybody. It is a pleasure for me to be here. I had the opportunity to participate last year in the workshop organized by SESAR Automation Task Force. And yes, today I will give a short overview of the current research topics in artificial intelligence, and mainly put the topic of machine learning, which is the dominating paradigm today in the context of the short history of artificial intelligence in the last years. So please, in the next slide. Here we have the outline. I will give a short introduction of the current state of the research and fast visit to the main paradigms, crafted knowledge, that was the origin, statistical learning, and big data, which is the main trend these days, and contextual adaptation, that maybe is the future or the next challenge in research artificial intelligence. So I will visit these paradigms and give emphasis in deep learning. At the end, I will mention other paradigms, other research trends in artificial intelligence, like expert systems handling uncertainty, distributed artificial intelligence, or cognitive agents. And just at the end, only to connect with the following presentation, some connections with scenarios that have been proposed to increase the automation level in ATM. So next slide, please. Okay, so there is no doubt that artificial intelligence today, especially in the last 5-10 years, is in the media because it has achieved a very important success in some aspect that call for attention, for huge attention, especially when the automatic system defeat human beings and achieve success, for instance, in playing games against humans. So this always calls for attention. It's a good commercial strategy. So since more than 20 years ago, when IBM Deep Blue defeated the chess champion, Garry Kasparov, after that we have witnessed more milestones in this sense. 10 years later, IBM Watson showed the capability to win a quiz show, to replay questions, being able to access to plenty of information and reason about the context and get appropriate replays and defeat the champions in this show. Or more recently, the Go, considered the most complex strategy game, was also a win by an artificial intelligence program, AlphaGo, developed by Google, and beat the top player KJ 5 years ago. Besides that, we have plenty of attention in artificial intelligence due to huge investment from big companies, both in hardware, in architecture, especially in machines which are prepared to work with machine learning solutions, especially in the side of neural networks. So, for instance, we have the graphic processor unit. We have specialized devices to host deep learning solutions. We have servers dedicated to host and to apply this type of solutions. And at the same time, we have huge companies, Google, Microsoft, Facebook, etc., working with very big data sets to extract knowledge from this data set and show the capability. So the result is we have artificial intelligence in quotidian, in everyday applications. So we are all aware of the capability of these solutions, especially in a human interaction aspect, how they are able to understand images, understand sounds, voices, even to carry out some interaction with human, to keep a conversation, understand human natural language, etc. Or we have witnessed the development in robotics, assistant to drivers, etc. So this is the current context. Next slide, please. The first precedent of artificial intelligence, we would say, is the challenge of addressing the process of a huge data set in some specific domains, for instance, in astronomics, in climate models, in DNA. We have to access and process a very, very big data set to build complex model and carry out a classification or understanding task. We have moved to new application, new data streams, for instance, Internet of Things, where we have millions of devices providing a stream of data which have to be processed and understood. We have social data, which is one of the current trends, understanding and being able to manipulate this data to build models useful to do some very commercial important tasks. We have continuously new applications. For instance, when we refer to DNA and genomic data, we have a development of pharmaceutical drug discovery, new solutions, or personalized medicine. The other precedent to artificial intelligence, next slide, we have witnessed the very important progress in developing autonomous cars. We can mention to the DARPA research program. So 15 years ago, this is 2005, the second year of this event, we have cars which were able to navigate and move in desert and being able to avoid the obstacles and avoid the problems to carry out to the end. 2 years later, the challenge was with a coordinated problem with which is called urban challenge, since the cars were to be able to reason about how what was happening around in order to navigate and move. Here we had, yes, mainly the competition between the top American universities, Stanford, Carnegie Mellon, and the result was the researchers of these solutions then went to the Google self-driving car project. So since 10 years ago, we have witnessed the huge progress of this type of solutions of artificial intelligence and machine learning to give autonomy to the cars. So if we go to the next slide, please. If we take a look to the progress of artificial intelligence, we can identify what is called waves. In the sense, if the general objective of artificial intelligence is giving machines a capability to reason, to solve problems, inspire or mimicking human intelligence, we can distinguish a different type of paradigms that have appeared in the year. So the first artificial intelligence solutions were methods using handcraft knowledge, trying to replicate or to encode the knowledge from experts to reason with them. A second wave clearly appeared later with the emergence of machine learned methods, where the paradigm were more to take advantage of available experience, available data to build models and generalize in more solutions. And we can mention a following a need for a third wave that would be contextual adaptation, and also a need to look for generalization with an explainable process, trying to understand what's going on and justify the decisions or the reasons to take that decisions by the system. So if we look in the next slide, please, if we look to this table, here I highlight the waves and the distinguishing aspects. This is also a question of terminology. Deep learning, which is the current situation, is labeled by some authors that the extension of second wave, and for other authors, this is the third wave. I have preferred to follow the DARPA terminology, so this would be an extension of second wave. So the first wave, we would have the paradigm of logical rules to encode the expert knowledge in the shape of rules. There is no learning from data, so the knowledge is directly encoded from the expert, and the algorithm application is taking these rules and to derive decisions. The second wave, as I mentioned, from the 80s, could be the paradigm of machine learning, mainly or starting with methods derived from statistical strategies. The expert knowledge here is not directly encoded, but the expert knowledge is used to propose models and features. Features are the variables to derive the models, to reason on these variables. The learning is basically take the available data, available experience, and derive which are the parameters, optimal parameters to build these models to the enough accuracy. And then the application will be taking this model, this tuned model with the parameters to the new problems. And since in the last 10 years, more or less, since 2010s, an extension of second wave has been, which is called the deep learning paradigm, which is an extension of a machine learning, where we have also methods that can be more or less labeled in the side of statistical methods, where here the expert knowledge is only used to propose a model, but we leave the system to learn what are the best features. So that means that we leave the system the capability to automatically generalize, to build more and more general features to automatically reason and look for a generalization. And the mechanism is the same. Once we have these tuned models with a huge number of parameters and layers of variables to looking for generalization, we apply to the new problems to solve the tasks. Okay, so if we give a first visit to these paradigms, in the next slide, please. The first type of solution, the expert systems, they try to simulate the human reasoning, basically triggering the sets of rules to decide the appropriate decision. Typically, these were developed for narrow domains like a medical system, where we collected the knowledge from the experts in order to generalize and apply to give automatically a diagnosis. The problem or the weak aspect, they are not able to directly learn from data. So if this system commit an error, we have to manually correct, to fix which is the rule that has to be replaced by a new solution considering the data. So this is the brittle aspect to handle uncertainty in the self-generalization. On the other hand, the major advantage is interpretability. We can trace exactly which is the chain of reasoning taking a decision. So that is the good and the bad aspect of this first type of solution. They have been continued use. Currently, the paradigm of these systems is solution handling uncertainty with a generalization, with a combination of other paradigms like Markov networks, working with probabilistic methods, or fuzzy logic, working with fuzzy systems in order to embed the knowledge and also look for the origin of having the clear rules to explain the chains of reasoning. If we go to the next slide, the second wave, as I mentioned, would be the advance of a machine learning, that is method to solve problems by learning directly from examples and building models able to generalize. Machine learning are able to build a model that is able to give solutions to new problems once we have enough amount of data to train and to build the models. We have plenty of paradigms in this case. So we have explainable models, basically in the family of rules, inductions, trees, ensembles of trees, etc. And we have other models which are not explainable at all. And in this case, we have the neural networks that operate like black boxes. No, there are no semantics or no directly semantic that can be extracted from the models. We have the training phase, we build the model, and then apply. And this paradigm has been extended. Going to the next slide, please. Going to what is called the deep learning paradigm, which is an extension of this second wave. And here, the interest of research has been basically look for capability of generalization, but generalization done with an approach of putting more and more layers of hidden variables, which are grouped in these layers in a deep length from the input. So when we have deeper and deeper variables, we understand they have more capability to generalize and to apply these models to a new and different solution. So the strategy with this type of solution, we could say, is a raw or brute force approach in which we have many data in order to build this complex structure, this complex solution, and with an optimization process, tune all the parameters in all these layers in order to have a solution which is very general and provide the decisions or the solutions to a huge amount of situations. So we can generalize if we have enough data. So the main distinguishing aspect of this wave, we have multiple levels of representation. We have many layers. We increase the generalization capability. And we have shown, yes, that this paradigm has obtained the best results in some aspect I mentioned before that have called attention, that are capability of recognition, speech, and image classification, image understanding, extraction of voice from speech following conversation. And we have a spectacular success in the sense that they overpass the capability of human beings. So we have a system that more robust and more able to classify image and to understand conversation than human beings, and even extensions to natural language processing, capability to analyze huge amount of text and extract patterns and generalize from this text, enable to do a very complex tasks. Like, for instance, automatic translation or building stories, etc. If we see graphically in the next slide, please, the main feature of this paradigm, in this box we can see the progress along the waves of solutions. So the rule-based systems, those developed in the first wave. We would say that we directly have input, and from input we have a hand design program with all the knowledge encoding rules to provide the output. If we go to the next column, classic machine learning, here we would have the input. The input is pre-processed to provide a hand design feature, which are the variable to reason on. And from this feature, we have automatic machine learning to generalize and build a model, mapping from features to the output. And then we would go to this extension of deep learning where we look for automatic building of features. So from the input, we would go to looking for which are the best features, and from these best features, mapping to the output. And in the rightmost column, we would have the paradigm of a deep learning in which we have a chain of building of features, and over these features, new, more complex features in deep layers until we map from this chain of layers to the output. So we would say that the main distinguishing feature of this paradigm is looking for generalization as a chain of building new variables. And next slide, I try to give a very short summary. I think is well known. by everybody of the history, short history of deep learning, as you probably say. You know, the seeding companies working in this solution at industrial level were bought by Google. First, Google Brain, that was acquired in 2013, and DeepMind, which is the main company today providing solutions in machine learning based on deep learning, was a startup in developed in 2011 by these researchers and was bought in 2014. Very fast after this purchase of these companies, we could say results in the media, for instance, as in the next slide, please. They were able to beat all the image classification algorithms at that site, addressing the challenges of classifying a huge image data sets. In 2012 competition, this challenge over 15 million high-resolution images with more than 20,000 categories. They got the best result with a big margin. Or the following year, a more shocking result. They show the capability to directly learn from images in order to play classic games for Atari. So as we can see here in this slide, we would have directly learning from the pixels in the images. So we would have the images, and we would have a strategy called reinforcement learning, and the mapping from these raw pixels to the joystick to decide the best action was solved by a chain of convolutional layers of deep learning. So yes, very spectacular results and calling for attention. So we have these results in images and more success also in games. In the next slide, please. We also witness this capability of defeating human beings and playing games that require strategy and reasoning to win. Here, the most interesting aspect is the new strategy, the new process to build the models, that is by randomly generating many thousands of games and learning directly from this generated data. So this is a very interesting strategy that was totally new with respect to previous classical solution, crafting the human knowledge. Here the strategy was randomly playing many games and collecting this data to learn itself how to progress. And it was shown, yes, in the play of Go, as I mentioned, or in the play of chess. So in certain domains, in some closed domains, if we have capability to generate many data, we can build more and more complex models with capability of generalization, and was shown in these very representative games. Okay, so this is regarding the history of deep learning, and now just to close, some issues that are very well known by all researchers. The first issue is the lack of transparency. We have very powerful models, but we cannot explain how they work. So we have we have the impression they are very good models because we have used a huge amount of data to generalize, and we have tested with all this data, but we cannot explain. The performance is limited to the availability of data. This is the second issue. So if we want to develop these models, we need enough data, representative data of the domain covering all cases. And yes, at the end, we have basically what is called a black box. We have input, output, but it's very difficult to give visibility. So in this sense, a focus of research in artificial intelligence and outstanding, we can mention the DARPA agency has called for attention and labeled emerging the trend of research, which is explainable artificial intelligence. That means how to extend, how to complete these systems with an explanation, as we can show here in this figure. So we would have the model to classify, automatically label the images, but we are looking for explanation. So if the result, this is a cat, why? What are the main aspects in the line from the input to the output to give this solution? If we can identify some distinguishing features like whiskers, claws, fur in the image, or we have some patterns in the image like the ears here. So this is a current research line. So in the next slide, very summarized. Here is the intention. The intention of this, as I mentioned, is fostered by DARPA. How to complete the machine learning with explainable models in order to provide the user with information to reason about the solution. And this is very important in some aspects, and especially in domains where we have to take decisions implying safety or of danger. So this is a very, very important wave of artificial intelligence. In the next slide, here we can see, by DARPA 2, which are the features of artificial intelligence. So the emphasis in this third wave would be in reasoning and abstraction. So if we see in the first wave, we had perceiving and mainly reasoning. In the second, perceiving and machine learning. Here in the third wave, the focus and the strength would be giving more capability of abstraction and reasoning. And basically that means revisiting the paradigms and putting more emphasis in contextual models, how to explain the decision, the solutions, not only from the input to the output, but also representatively, explicitly the context and reason about the context. Okay, and just to close, only a fast view. There are other paradigms in artificial intelligence besides reasoning or machine learning. I only wanted to call attention for what is called distributed artificial intelligence. That means many agents, many algorithms working in parallel. And call the attention to what is called multi-agent solutions. So they are like a branch of distributed problem solving. Here we would have two branches, which is parallel artificial intelligence, many divisions working in parallel, and multi-agent system that put the emphasis in interaction, how give autonomy to its component and how to coordinate. So in the next slide, please. Only graphically represent the problem. It's a problem of giving autonomy, giving responsibility, multiple nodes to coordinate and to have a piece of the environment, and how to give each node the capability to reason about what is perceiving, and the decision has to be coordinated with other agents in the space. If we the next slide, if we go to the this is the old paradigm, but it's very related with the open issue of explainability and giving capability of justifying and reasoning. It is called cognitive agents, and the model is the belief, desire, intention. So this is a community of artificial intelligence working in this explicit representation of reasoning of agents that operate in a certain environments, but have this capability of representing in a logic way intentions and model to give the solutions. And finally, if we go to the next slide, we would have like different families of agents. Some would give a fast mapping from input to the output, that they are called weak agents, and we had in the side of a strength agents, in the side of having a cognitive model, a explicit representation that would give capability of tracing the chain of reasoning to derive the solution. So we would enhance these agents with capability of coordinating and providing collective behavior with mentalistic representation notions of plans, goals, beliefs, in order to have a more controlled understanding of the solutions given. So this is a paradigm that is very appropriate to addressing complex systems. And in the next slide, just to close this paradigm, please. The designing of this type of solution have to work with concepts in the side of complexity with complex systems. So basically, here we would have like two main aspects to take into account, which is the emergent behavior, the self-organized criticality. That's a complexity that always appears when we have interaction of many systems in uncertain or not predicted situation. So it is an observation process to analyze the behavior. And on the other hand, we would have a design, we have an engineering process in order to analyze all the reactions, all the type of behaviors appearing, and we have a tuning, evolution of the solutions in order to control the complexity of the system and give the desired reply accordingly to the desired output in each situation. So this is a aspect that always appears when we have a distributed approach to address this type of problems. Okay, so with this, I would go to the, only to connect with the open scenarios indicated in the last year in the SESAR automation task force workshop. They mentioned these three type of scenarios, and we could relate the paradigms of artificial intelligence research in order to look for the specific solutions accordingly to the expectations or the level of autonomy that we give to the different inputs. So we would have here, the different problems mentioned of giving machines the knowledge of experts, giving capability of learning from situation, and the last aspect, giving the capability of coordination and interacting between different problems. So with this, I would go to the conclusions, just to finish. Basically, to highlight the aspect I have mentioned in my talk. So we have, a very remarkable success. We have plenty of cases and results where we can see that the deep learning, machine learning paradigm is getting success in certain challenges. We can see spectacular results in robotics or in driverless self-autonomous cars. We have very interesting results that can be transferred to other domains. As a weak aspect, we could say that most of the successes can be described as narrow domains, in the sense that we need a very clear definition of tasks like classification, regression, grouping, etc. And we need a representative set of data in order to have a reliable model. I have mentioned the current challenge of artificial intelligence is giving capability of explanation, transparency, in order to be used in some critical application where we need to take important decisions, and we need to explain how the system is working. And at the end, I have mentioned, the open problem with the paradigm of a distributed artificial intelligence, where we have to put an eye on interactions between different autonomous systems that produce emergent behavior, and we need also a methodology, design tools to guarantee a robust output, a controlled performance of the system. So with this, I close my presentation. Thank you very much for your attention.
Thank you very much, Jesus. That was very valuable. I think that for the people that are less familiar with artificial intelligence, may have been a bit much. I definitely appreciate it. Just to as background information, I did mention at the beginning that the scientific committee has written a report based on the workshop from last summer dedicated to this topic. That report will be out on our website very shortly. It is not at the moment, but it will be shortly, so that you can read in depth everything that Jesus just explained. Thank you, Jesus. Up to the next speaker, which is Mark Baumgartner from IFATCA, from the controller perspective. And I'm very curious how a controller will respond to this kind of thoughts about going to fully autonomous systems, whether it should be hybrid or not. What about using systems that are not explainable? How do you see that from a controller perspective, Mark?
Thank you, Ruben. Can you hear me?
Yes, we hear you.
Okay, so I'm going to share the screen, and hopefully I will be able to address some of your questions during the presentation. First of all, thank you very much for having allowed me to make a couple of reflections and slides. The title of my presentation is The Joint Human-Machine System, the Only Way Forward. So basically the message of today is, of course, it's wonderful to have all this machine learning and artificial intelligence being made available, but don't forget that there is also a human, or that there are humans around, which there is a new way of working with this new technology. And basically, conceptually, I'll present something we have started to create at IFATCA, a concept which is called Joint Human-Machine System for the ATM, and we call it the only way forward. So as mentioned before, in IFATCA, we have basically started all the times, but in 97, 98, we started to look towards the 21st century. We presented in 2007 a global statement on how we see the future of air traffic management at the global level. We have worked together with Airbus, with the pilots, on automation issues in the field of air traffic management. We have also been able to co-write the role of the human as a chapter in the European ATM masterplan. And since 2017-18, we have started to organize dedicated workshops on the future challenges. So in 18, we had the operator in the system. We also had a look at what are the possibilities and the limitations of the new technology. And in 2019, we have introduced this joint human-machine system approach. For this year, there was also a workshop planned, and that was on remote tower, but that unfortunately, due to COVID crisis, we had to postpone that. So out of these workshops and out of the brainstorming session we do, you will have accessible under the IFATCA websites and publications, where we explain a little bit in detail what I'm going to talk to you in the next 10 minutes. So if you have a mind map approach, then this would look a little bit like this. I will not touch on all the topics, but basically the chapters are, we need to define, in order that we reduce misunderstanding. So we need to define what is it, what we're talking about, joint human-machine system, but also what is it, artificial intelligence, big data, digitization, what does this mean? So there is plenty of things which are currently still a little bit buzzwords and maybe not yet explained. And we need to actually secure active involvement of the human. That has been also outlined in the presentation of NATS, that this is one of the biggest challenges, that you get the people who will in the end use the system, or in the end be subject to certain of the results of the artificial intelligence, that you need to involve them from the outset. The societal problems, so liability versus safety, who is in control, how do we bring everybody together? So from the design processes, programmers, how do we make these people who are not necessarily talking to each other work together? Allocation of functions, I'm going to touch on that. And also, what is autonomy? Define what is autonomy. And certainly also something which we need to explain from the sector is that we have some sort of negative image from the past when it comes to progress, to change, to acceptance of change, and things like this. So that's certainly a homework for all of us working in air traffic management. it is not just a fashion. It is there to stay. So modernization of ATM system will be the cornerstone of the implementation of Single Sky initiative in the future. We will be maybe we are too late, but maybe we're too early. We really do not know that, but certainly we can't just talk it away. So it will be there, it will stay. Now, also in parallel to all the technological possibilities and the machine learning possibilities and the computing possibilities, you will also have to address what kind of business model you will want to see when these new potential applications to hit the ground. In just here to go back a little bit in history, we were inspired by the automation philosophy of the aircraft manufacturer. When the aircraft manufacturer moved to more automated airplanes, and in 2003 at a seminar, which was actually the founding seminar for the concept we know where they have in the ATM master plan of SESAR, we actually established some sort of 10 commandments, which are still in a way or another now flowing into the current concept of the joint human-machine system. So automation is not old if you look on a time span, but it exists for quite some times. And I'm here showing some of the first computer, but also the Turing machine and so on. And this is very important to understand that we have already artificial intelligence and machine learning in the system. So you see on the right-hand side some arrival time research projects led by Eurocontrol or SESAR, and also automation is not really new. We have conflict detection, we have resolution advisory, we have plenty of things. However, when it comes to the backbone in the back, we still are working with some of the very, let's call it, old computer system, and that is certainly something where we also will see tremendous changes. Then of course we have some sort of liability issue, always safety first, and these are things we need to actually think all together. There's blockchain technology, which certainly would also help and assist to overcome certain of the blockages which safety could create. And then there's always something which we also need to keep in mind, and that is also not new. We always imagine the real world, the one behind me, for example, different than what actually happens. And when we talk about cybernetics or things like this, we also have to understand that we need to tame complexity. On the right-hand side, you have a small picture on what exists: work as imagined, work as processed, work as disclosed, work is done. All these things will not go away, but we will have to learn to work with it all together. And then you will always have the natural tension in the system: air traffic controller versus change. So, and then the regulator versus platforms, incumbent versus disruptor. But all these things, if we look at it a little bit from the outside, is not new. But there are people also in the sector who are maybe not that familiar with the ins and outs of the technology available, but also of the operation concept available, who think that all this is very new. And then also what we have learned by looking at other sectors, by inviting the other sector, the medical world, but also the logistics world, the aircraft and systemic science into our workshops, we have actually learned that we are behind when it comes to automation technology, but we are actually not behind in terms of technology, but in the use we make of it. Given all the airspace, all procedure and the safety first cut, we do not really make the most of the technology which is available to us. When you look at the aircraft and aircraft cockpit and the amount of technology, most of that is not being used on the ground by ATM under the claims that the data might be wrong. So we are actually sometimes hindering ourselves. And if you look at fully automated systems where approach and tower units can show each other with automated paper strip or e-coordination, things like this. But then when you want to release, you have to pick up the phone and you have to call your colleague and give a release. So these are certainly things which we need to address and learn from the other sectors how we could use some of the available technology there. A traditionally approach when we implement new technology was men are better at and machines are better at. So this is something called MABA in a jargon, and depending on the level of automation, the task was more or less distributed to the human or the technology machine. So the current thinking in next-gen SESAR, but also in IK or ASBU, has been very much influenced by MABA, but also we, all the humans who are working in the sector, are still a little bit tainted or basically influenced by that. So what is the joint human-machine system? It's basically bring the human together with the machines, the big data, the Internet of Things, into one. And this is easy said, but it's quite a complex thing. So if you have, for example, here, you see that the machine is some sort of trying to control human versus machine. The human manages the machine, or vice versa. The computer on the left says here, and the worker is trying to imitate the movement. Whereas on the right-hand side, you see a picture from Hyundai where a person has a robotic suit, which allows him to carry much more weight than he normally can do. So this is a combined thing. In order to structure the thoughts we had at IFATCA, we teamed up with the University of Applied Science and Art of Northwestern Switzerland, and namely with Professor Tony Waffler, and he has been the one who has presented these slides already at one of the SESAR seminars. So what do we mean by this? Actually, there is on the left-hand side some competition. So that's what we actually are experiencing sometimes. The human manages the machine or vice versa. And on the right-hand side, what we actually would like to say is to see in the future, it needs to be together. So it's a function which can only work together. And joint cognitive systems can be described as goal-oriented, adaptive, views problems in more than one way, uses the knowledge about itself and the environment, and maintains control of a dynamic process. So these bullet points set up by Holnag and Woods what do they mean in other words? The human as such is not a user of the system. The human is an active part of the joint cognitive system. So very important, human does not interact with the interface. The human interacts through the interface with the process. So in joint teaming, here on the left-hand side, a picture of artificial intelligence, muffins, dogs, puppets, and things like this. So very impressive what artificial intelligence and machine learning can do. We have heard that before, but actually also what we need to keep in mind, here's some statistics on everyday maths, that you still have adults who can calculate much better than the artificial intelligence, but the machines show amazing capabilities, but still the humans and the machine are complementary. We should never forget that we will always have humans in the environment where the machines are working. The machine has a deep knowledge, calculates, may give good answers, and the human has a cross-linked knowledge, thinks, may ask good questions as well. So that's the joint teaming we do see. What is the human contribution? The human contribution to the joint human-machine system is the verification of technical decision. He can improve technical system, learning from the technical system, and he's very good in managing uncertainty. He takes responsibility, shows commitment and dedication, and of course has some empathy, creativity, and can improvise where needed. But for that, you need to, of course, have a few preconditions set up, and you need to give the human a clear role in the system. You also need to have a system design which is respective. That means that you avoid de-skilling, that you allow continuous development of expertise, and that you also design the jobs. The job design is really required, and the ergonomics go far beyond that, just the interface and the user's experience part. And a participatory participatory approach is a must. So this is the human contribution to such a joint system. What are the goals of the joint human-machine system, if you wish? It's a closer collaboration between the operators, system designers, system decision makers, and the public. The human and machine complement each other to achieve system goals, and a humanistic design that allows humans to recover from the rare high-risk scenario. So again, the automation should not be human versus machine, but the automation should be seen as a human-machine coordination as a team. What is further needed? The future technological improvement need to focus on the system rather than the components, and on the task rather than the structure, to be able to cope with the complexity and the deliver of the expected benefits. A participatory design or cooperative design that actively involves all the stakeholders, in particular the employees, the partners, the customer, in the design process to help ensure the result meets their needs. This is certainly something which is very challenging in the way as well. We have set up some sort of a silo approach when it comes to technical improvement. Towards the end of my presentation, a few inputs, food for thoughts. In order to have Jeff Koons' dog created, you need 90 people, but you need also about 80 to 90 people to run an unmanned aircraft. So what seems to be a pilotless aircraft here, in order to run it as a system, you need to have 40, 50, 60 people working on it. You also have the challenge that the development, the introduction of this new technology needs to be done in a system which is running 24/7. So this is also something which is creating some sort of challenges. Further, you will always have surprises, and they will be part of the day, because you don't really know. We heard before, we can't really explain some of the machine learning or artificial intelligence results. So what kind of rhythm suddenly with the changes will come in? How do you change these rhythm and so on? What kind of surprises will force you to do one change maybe in 3, 4, 5, or 6 times? And then, of course, you have something which we don't know in ATM, the trial and error approach of the programming of the computer environment, which we don't really know. So that's something which also we have to learn about. The multifunctionality, this is also something which is very important. Sometimes you should not try to have the magical golden plate solution. You should have very small elements instead of creating a tool which is multifunctional. Maybe you just automate or try to automate a few small things. And then something, when you look at a complicated or complex system like this in the future, you will have much more actors interacting with each other. So the dependence on each other's is very, very important. And that's something we are maybe for the time being, as we are a bit in closed systems, are not aware of. And we should also be we should be also aware that there's a lot of buzzwords and there are a lot of commercial activities around artificial intelligence and machine learning. And this is certainly something we need to focus a little bit also. What small successful steps can we take towards machine learning, and so on and so forth. This is maybe, sometimes I call it as well, it's overrated or underrated. So some of the automation processes in ATM are wonderful, and others are very promising, but in the end, for various reasons, they don't work out. And then there's also, we are still sometimes being trapped or prisoned by the 7 deadly myths on autonomous systems. So this is also something we need to keep in mind. A few of these food for thoughts for further discussion. And here also a general comment. If you look at the 737 MAX, 800 MAX, this is typically something where the human was there by design. The human worked, the machine worked well until a certain envelope, and up beyond this envelope, it was nearly no more controllable. So these are challenges we will face as well in ATM when we start to look into more artificial intelligence, more computer power, and more machine solving programs which will assist our daily work. Thank you very much.
Thank you very much, Mark. That was very useful. I'm glad to hear that even from a controller perspective, you think in terms of cooperation and not in terms just of competition. I think that's definitely a very proactive and a good way forward. You also introduced the topics actually that EASA will probably see as challenges in particular in the fact that if you move to cooperation, you're redistributing responsibilities. You also mentioned safety, liability, and I could imagine that if you look at it from a safety management perspective, that introducing a whole team behind to work on the artificial intelligence and work in an operation environment in a collaborative mode between artificial intelligence and the controller, that actually leads to changes in both in certification, in safety management, and in liability as well. And with that, we'll hand over to Guillaume Souda from the European Aviation Safety Agency to give us some light on that. Guillaume, please take the stage.
Yes, Ruben, thank you. Can you hear me well?
Yes, we hear you.
Excellent. And I just will share the screen. Okay. So good morning, everyone. So I am Guillaume Souda, software senior expert and AI project manager at EASA. Can you see the slides, Ruben? It's all fine?
Yes, we see.
Okay, perfect, thank you. So I'm glad to be with you today and to have the opportunity to present some of the progress we made since we published our EASA AI roadmap. And the slides I prepared for today are going first with an outline of the organization of EASA around innovation. Then I will give an overview of the EASA AI roadmap before digging into the center, I would say, of the presentation, which is the AI trustworthiness concept as a driving factor for the roadmap. And then I will focus on a specific building block of our roadmap, which is the learning assurance building block, before opening up for further perspectives. By the way, I didn't mention, but the EASA AI roadmap, in case you didn't come across it yet, is available on our website under our artificial intelligence page. So feel free to download it. In 2018, EASA has launched an internal innovation network to deal with disruptive innovation. It looks like this, with at the center the innovation cell, which through this innovation network interconnects the different directorates of our agency. So the executive directorate, the safety management directorate, certification, and flight standards directorates. And the goal of this innovation network organization is threefold. You can see that on the right-hand side. First, to support the industry on innovation through partnerships with innovation partnership contracts, which is a new type of contract we created specifically to deal with innovation with our industry partners, and also through a memorandum of cooperation. The second objective is to create a dynamic innovation within the agency to foster sharing of information and knowledge around innovation topics. And the third point, or third objective, is to manage and coordinate the changes that may be necessary within the agency to deal with innovation. So the first key topic that has been tackled by this innovation cell and innovation network is artificial intelligence. So end of 2018, we created a task force, a small group of people working towards a roadmap by analyzing actually the impact of artificial intelligence in the various domains of remit of the agency. And we came up with this roadmap early this year, in February 2020, with a clear focus. It's a V10 of the artificial intelligence roadmap. Means we may, of course, in the future, revisit this roadmap and focus on more aspects. But so far, we have really put the focus on machine learning and deep learning, which actually corresponds to a lot to what we heard so far from Jesus in his presentation. Now that we started implementing this roadmap, we needed to create a much wider team And the way we've created this team was really to select people and experts in the various impacted departments within the agency. So you can see again the organization with the directorates, the innovation cell, and people are really gathered from the supporting and operational departments within the agency. So you may know some of the colleagues. And you're probably also familiar with the EASA AI roadmap. I have just extracted one slide here to provide you an outlook on the timeline and the major milestones of the roadmap. So this roadmap is based on industry roadmaps. The one at the bottom is an example. It's based on commercial large aircraft transport operations. So we could have totally other roadmaps at the bottom, for example, the ATM automation roadmap or based milestone. The first one is in 2025 with the first needed approval for machine learning solutions. And then when we talked with Airbus, Thales, the major players in the field, let's say, of more autonomous operations, they are targeting for single pilot operations in commercial air transport by 2030 and more autonomous, full autonomous operations by 2035. The dates might change, and this is not the major point. What we tried to set up is a first phase of exploration and first guidance development to be able to be ready and to meet the deadline of 2025. We will ramp up actually slowly over the years with first usable guidance with 3 different levels of AI, which actually reflects also the discussion that Mark had before on the more collaborative way of dealing with machines. So the first level is human assistance and augmentation, where the human is fully within control and is assisted by the machine. And then we will ramp up to a level 2 with more human-machine collaboration. And that's where everything that Mark mentioned on his slides is really important to consider. And then in a level 3, we will go for more autonomous machines. And that guidance should be available. After, we will enter a phase 2 of consolidation, meaning more formal rulemaking. But because of the phase 1, we will have probably a very efficient way of dealing with the rulemaking, and so a rapid capability to deploy guidance, means of compliance within our regulatory framework. And we have foreseen, not yet completely planned in a detail, but we have foreseen a phase 3 for pushing barriers, because of course the AI and machine learning field of research is extremely dynamic, as Jesus could also show, and this is something we need at some point to adapt to. So that's an overview of the roadmap. Now, coming at the heart of the presentation on the concept of AI trustworthiness, which is the main driver of our EASA AI roadmap. So by nature, we can consider AI and machine learning agents, I would say, as a black box. Trusting the machine learning agent will involve opening this box to a degree that is commensurate with its intended use. And that's the driver we took to create this AI trustworthiness concept. And to enable actually the conditions for approval of AI and machine learning, some necessary building blocks have been identified. And that's what you can see also in our roadmap. Here, this is the result actually of the impact assessment we've done in the various domains of the agency. It's really not focused only on one domain. It's considered that actually these 4 building blocks will be at least necessary to be able to go for approval or certification of safety critical applications in any type of application in aviation. When it comes, of course, to be safety critical, that's one of the key criteria. The first block is the AI trustworthiness analysis. This is, I would say, a gate and a way to translate the ethical guidelines we received from the EASA, from the European Commission, high-level group on AI. And of course, those guidelines are quite high level, so we need to translate them into something practicable for the aviation domain. So that's one of the first aspects. Then we have 3, I would call, more technical building blocks: the learning assurance, explainability, and safety risk mitigation, which we represented with potentiometers here, meaning that we might not need to push the potentiometer to 100% for all of them. It will depend on certain criteria, like the level of AI, like the criticality of the application, etc. All of that to be set together, and the learning assurance block is about the paradigm shift that we could see from programming, I would say, to learning. We know a lot development assurance. We have development assurance frameworks available today, but they are not totally adapted or not adapted to learning processes. So that's where we are digging into this aspect now to create guidance specifically for learning processes. The explainability building block is a very important one. It deals a lot with the human-machine interface, and that's the place where we consider that trusting a machine and an AI or machine learning agent will necessarily go through the capability to understand and in an explainable way the output of it. And that's the whole purpose of this building block. The safety risk mitigation building block is in the first thinking more traditional type of safety nets to mitigate the risk in the case where we might not be able to open the black box as expected through the two first building blocks. So I now will dig actually a bit more into learning assurance and where we headed with that. So we have created a W-shaped process, which is to answer the question how to ensure confidence in the functioning of a machine learning application. So this builds on the traditional V-cycle process. We created a W-shape because of specificities, I would say, of learning processes. And the very important thing to say is above the dotted line, we are still in requirements management, requirements verification, so more traditional development assurance framework, so like a flow down of requirement. But at some point, we will meet with machine learning, with the nature, I would say, of machine learning solutions. We will need a very important step of data management, and then a management of the learning process, a verification of that learning process, before going into an implementation of the model. Oops, sorry. And before being capable actually of verifying by ramping up here the inference and the final implementation of the function. Of course, the safety assessment process is a very, very important integral process to all of what will happen in this W-shaped cycle. In order to investigate this more deeply, this cycle and this notion of learning assurance, we teamed up with a company, Daedalin, a Swiss-based startup, which is specialized in computer vision solutions for aviation. And we created a report together with them. We had two objectives. The first one was to mature selected key aspects of the concept of learning assurance. And the other one was to investigate the embodiment of AI performance in safety analysis. So we did an exercise actually over the period June 2019 to early February this year. And to provide you a bit more context, it was the first IPC, so innovation partnership contract from EASA that was dealing specifically with deep learning. And Daedalin brought their expertise in computer vision and deep learning, and we brought ours in safety, certification, and ops. And the result, first, before talking about the result, this is a brief introduction of the use case to give you more technical context. So the system studied was based on a runway detection system, based on a high-resolution camera that provides, after some pre-processing, images to a convolutional neural network. After some tracking filtering, the output of the system is whether there is a runway in the field of view of the camera and where it is located, so what are the coordinates of the corners, of the four corners of the runway. The convolutional neural network, I'm not digging into details, Jesus would do much better than I would, but it's merely doing some convolutional, it's a type of neural network using convolutional filters to be able to better identify some shapes, contours, and things on images. So with that, we now focused actually a lot the IPC, so the Innovation Partnership Contract, on the data management and learning aspects, and focusing now on data management. It's clearly a key process. I mean, everyone will understand it because data is the source, the fuel of everything we try to do with machine learning. We introduced the notion of data quality attributes regarding accuracy, resolution, assurance level, traceability, timeliness, completeness, formatting. And to focus on one of the most essential ones, the completeness, it has a huge importance in the capability to give a guarantee on the generalizability of a neural network. And what the solution that is provided in this IPC as a possible way forward is to use a distribution discriminator, meaning slicing the operational state space in pieces, so in hypercubes, and to try to ensure a coverage of these hypercubes by verification of the completeness of the data set. And relying then on mathematical theorems that are available actually for a long time, we can, from the statistics perspective, we can guarantee certain generalization bounds. Maybe not to the point we would like today, but it's a path to investigate further. And this generalization guarantee, we see it as a crucial characteristic for neural networks to ensure the confidence that the machine model will perform as intended. Why is it so important? Because generalization is some sort of anticipation of the operational capability of a neural network, and that's the reason why it has such an importance in what we do in learning assurance. So the next, we made the first major step, I would say, with this IPC and with the work we've done so far on the learning assurance aspects. Now we are in a step of turning this into first available or first usable guidance. This is what we'll do. We're also starting working much more dedicatedly on the AI trustworthiness analysis building block and on the AI explainability building block. And I wanted to mention that we're also involved in the joint EuroCAE SAE working group, the WG114 G34, and in several research projects. And all of that contributes to meeting our first essential roadmap milestone, which is to public consultation, a first set of usable guidance for machine learning applications in Q1 2021. So it's a challenging target to meet, but we will try to reach that. I thank you very much for your attention. Very glad to have been able to participate with you. Unfortunately, I have a hard stop, so I will have to leave you and cannot participate in more questions and answers session. But feel free to contact me and contact us, because we are really a team behind. And I have put my address here on the slide. Thank you very much.
Thank you very much, Guillaume. Very happy to see that EASA is also starting to take good initiative in understanding how to deal with this new developments and actually having a pragmatic roadmap in the way forward. Very happy to see that. I do realize
Thank you very much,
that
Ruben.
in terms of time management, we're actually running late. We are now 9 minutes past our official end of the webinar. I do notice that we still have quite a lot of people online, so I suggest that we continue a bit for some questions. I do not see any explicit questions for you at the moment, Guillaume. So, well, maybe with the exception.
Okay, so as I said, don't hesitate to send me an email. Really, if you have any question or any suggestion. Yes, unfortunately, I have to drop now. So thank you very much, Ruben, and all for the opportunity. Bye.
Thank you very much, Guillaume.
Thank you.
Then I would like to ask all the speakers, with the exception of Guillaume, who just left, to come on stage so that we can go through some questions and answers. Claire, Andy, Jesus.
Hi, Ruben. I'm also going to need to go fairly soon. So,
all right.
If anybody's got any burning questions, please fire away.
Well, I think I saw the two of you already answer a couple of questions that came in during your presentation. So let's start with Andy and Claire then. You have already answered quite a few, but maybe in general, if you have any thoughts that you want to share triggered by the questions that you have here. I look in particular at questions that relate to the reliability of data, for example. Maybe you have something to say about that. I mean, I understand that you have been looking into or you have been working on multiple data sources to do your decision support for time-based separation. Maybe you can, now that we've seen the presentation from Jesus as well and the presentation from Mark and Guillaume, can you make the link from Nat's perspective on this about the level of which wave of artificial intelligence you've been applying here? What were the responses of the controllers in terms of trusting this device? And how did you do the certification?
Okay, so I'll take the in terms of the controller trust for the tool. That was a key element of the development. We had a core team of controllers involved in developing the system. We also involved the airlines and the airports and the regulator at an early stage of development, and I think that was absolutely key in developing the level of trust that we have. There are a number of things that you need to get in place, and I think the key element to success is getting all of the stakeholders to work closely together around a change like this. So and identifying the key issues that we need to address, like we needed, to be sure that we had quite high quality wind data. We needed the airlines to improve their compliance with ATC speeds on final. And we did a big campaign with the airlines to do that, aided by the airport. That was very successful, which then helps the controllers trust the information and also trust the fact that when they ask an aircraft to fly 160 knots to 4 DME, that it's going to do that. So I think the key learning that we've had is really the importance of engagement, and that started, of course, with the work we did with through SESAR in the first place. Provided a very sound foundation. In terms of how we use AI or machine learning, the tools that we've implemented are really around automating some complex tasks for the controller. And the next steps that we are working on will include things like the ability to be able to provide support for multiple transitions to a single merge point and things like that, which is quite a complex task for a controller to manage. But given that we have a very accurate wind model and the tool can take into account compression as the aircraft turns through the transitions, then that level of decision support for the controller is really, I think, will be a game changer. And then, of course, using machine learning to help maintain the parameters that we have within the system. So at the moment, that's quite a labor-intensive process to look through data on a regular basis and make sure that the tool is still properly tuned for the airspace and procedures. So using machine learning really in that, and we are getting support in Wave 2 for the pairwise developments at Heathrow. We're very appreciative of that, and that will start to use things like looking at all the factors that drive runway occupancy time, because as you start to squeeze the separations up more, then the runway occupancy becomes a real pacing factor. So we're early in that development, but that is something we expect to do over the next couple of years. Be able to demonstrate, very much tighter control and application of ROT within the tools that we've developed. So hopefully that goes some way towards answering the question you posed.
Thank you very much, Andy. Claire, is there anything you want to add from your side on the questions that relate to the models used and the input data?
I think in terms of, I think one interesting thing that's come up is over the presentations is that if you take ORD, for example, it's characterized, it is assured between sort of certain parameters to make it efficient. There is still the controller in there. So like Mark's presentation was saying, where you've got this working together between sort of the machine and the controller in this case. I mean, it's set such that it's under a certain set of parameters. Now, if the controller has additional information, for example, the lead aircraft he may know be particularly slow, then the controller can use their judgment, their expertise to modify it. So in that case, would leave additional separation behind the indicator. So saying, although we're providing tools to enable the controllers to deliver the separations more efficiently and more resiliently, they are still using their judgment to help in those sort of variable or more varied conditions that maybe are difficult to assure totally within the tool itself.
All right. Thank you.
Thank you.
Jesus, I see that you're connected again. You dropped out a couple of times. So now that you're on stage, I'm going to take advantage of that. I see one question that was, I think, was filed when you were speaking about can algorithms from the second or third wave be used to determine rules to be used for the third wave interpretable algorithms? I suspect that it's related to the wave 3 plus about making deep learning explainable, but probably you can shed some more light on that. It's the question from Pascal de Ketelaere. And I don't hear you anymore. I think your internet connection is lost. Okay. That doesn't work at the moment. Let's wait till Jesus comes back. Meanwhile, let's continue a bit. Mark, since you're here, let's just one moment. I see Jesus coming back up. Jesus, you're back.
Yes, I'm back, but the system is, my computer is not stable, sorry. Yes.
Okay, never mind.
I was looking for the question regarding the... Okay, I'm sorry.
So the question is from Pascal de Ketelaere. Can algorithms from second or third waves from your presentation be used to determine rules to be used by the first wave interpretable algorithms, so the expert systems? You can't find the question?
Yes, sorry, I cannot find the question, sorry.
Well, you know what? Let's forget about that question, Jesus. Let's just have the debate right here. I think
yes, okay.
It's a bit related, also related to the presentation of Guillaume, where EASA is trying to understand how to deal with the fact that deep learning is not always explainable. But I also saw in your presentation that you're actually moving on, or you're showing that there is development moving on towards a next generation of deep learning, which does actually explain or make explainable the layers in between. Where we saw the ears of the cat, for example. Do you see that there is any advantage in that development, in particular for certifying and doing safety assessments?
Yes, the problem is with this yes, with this type of models, it's really difficult to build the the semantics associated to all these connections and all these synthetically generated variables. There are other alternative models that try to increase the semantics associated to the model. I didn't mention in the presentation, but some explainable models that try to generalize with a more understandable models, for instance, in the ways of programs, in the ways of rules, so that there is a process in taking the data and building this, they are called generative models. So we can understand how these generative models synthesize from the learned data and then apply. For instance, there is a very interesting example is in handwriting domain. There are models that try to have a explainable model of how the system is able to recognize new examples by generating more. So the generative model is able to generate new samples, and they are compared with available data set. But they are like alternative models. The point is, with the deep learning approach, is really difficult to build a semantic explanation of the meaning of especially the internal variables used to generalize.
Okay. Thank you very much, Jesus. I think it's clear that there is still some research ahead of us before we can actually make the connection all the way to the work of certification and safety assessment. The next question for Mark. I see here that there's a question here about level 3. I assume that is level 3 of the ATM master plan levels of automation, is that the AI starts being responsible for certain tasks. Within those tasks, the AI not only proposes actions to the user, like decision support, but also takes decisions on those actions and implement them. Is that correct? Now, it's not necessarily a question for you, Mark, to explain the ATM master plan, but in this context, I think what I would like you to elaborate on is the fact that Jesus has explained different waves of artificial intelligence, which is not exactly the same as the table that we have on the levels of automation, which is more tightly connected with your presentation of allocation of tasks. But maybe you can elaborate a bit on your view of how the differences and the relationship between the waves of artificial intelligence and the levels of automations in the master plan.
It's for me as an operation person very difficult to answer this question in a competent way, because I mean this is conceptual engineering, also project management approach, which of course is needed. But for us, what is very important is that we have now the computing capacity, we have now also the experience, and you have seen that through the presentation of Nats. Every approach running through the system gives data, increases the stability of the system, provides new clues. So with that, you are starting to build up a big data set, which in the past, most probably the data was lost. Whereas now, because you have machine learning and artificial intelligence in the background working, you are increasing the understanding and the granularity and of what is going on. And typically, what we do expect, at least at IFATCA, is that for the time being, nearly everybody has assistance of conflict detection in an en route environment. If I may, I will just show you quickly what does that mean on an operational radar screen. I hope it works. Let me turn that around. So this is the radar of currently what is flying over Geneva. This is not an active sector, so you won't see that many aircraft, which, for example, are now in green. And here I have a conflict manager window, I don't know if you see that, which tells me what kind of conflict is to be expected. Because if the sector is not active, you won't see this displayed. But that has reduced, just to come back, that has reduced by 20, 30, 40% the workload of the actual air traffic controller. With that, we were able then to increase the capacity to actually provide more of a service of productivity to the system. Now, having done this, we need to go one step further, and I think Eurocontrol calls it CORA, Controller Resolution Advisory, where we would then ask a system who has learned how we, together with weather, in different situations, in an en route environment, are solving the conflicts the machine is showing us. The solving of the conflict would then be done by suggesting to the controller where he actually has to send the aircraft. If that is wave 1, wave 2, wave 3, if it's done with a deep neural network, if it's done with a Hebbian network, we really can't expect to actually have an opinion on that. But what we certainly have an opinion on it is how many times does a conflict detection or a potential future conflict resolution tool fail? So how many times do I need to interpret, do I need to come into play? And I think these are the challenging part. If that is transparent or not for the controller is not as important as for the ones who are actually programming. And I think this is also very spectacular when you say, the machine does something, but I don't know why it is doing this or why it has given me this result. So that's also something which for me, Jesus has also shown, where you don't really understand why the result is it. The result is not wrong or it's within the expected, but why is it like this? And this is also something in active air traffic control. You can't say, well, we have 3 missed approach because we don't know what the artificial intelligence did in the background. No? So that is. But I'm sorry, I can't really reply to your technical, more theoretical question.
Okay.
Ruben, can I just add one thing?
Andy, go ahead.
And just to follow on from some of what Mark was saying, you can't manage, the old adage is you can't manage what you can't measure. So it is crucially important that we take the data out of the tools that we are putting into operation and then use that to help manage our operation. And I think that this is one of the advantages of putting the automation in, is we have a much richer data set that really helps us understand what's driving our day-to-day performance. So, I thoroughly agree with that. I'm really sorry I have to go because I'm due on another call. So thank you ever so much for the opportunity.
We are also going to conclude here. I think we have now run half an hour over time. So if you bear with me one more minute. First of all, to the audience, thank you for having been listening in. The questions that you've answered here will further be answered, will be made available with the webinar, which will be published. The recording of this webinar is going to be published on our website. Also, keep in mind that on Friday morning, there's going to be the second part of this webinar, which provides another 4 examples of both exploratory research projects, industrial research projects, and 2 implementations of actual machine learning to improve capacity management and complexity management in an operational environment. So keep all in mind that has been discussed today, because that forms basically the background of those presentations, but it will make it more practical. To the speakers, thank you so much for having volunteered to come here on stage. I really appreciate it to have this debate with you and share that with our audience. Thank you very much. And with that, I'm going to conclude the webinar. Thank you all for having listened in, and hope to see you on Friday. Goodbye.